and this is on your screen. You can see this was the structure of CSTR. Here Fi, Ti, Cai. Fi was the flow rate. This was the volumetric flow rate. Ti was the temperature inlet, and Cai was the concentration of the reactants which are coming inside this tank. And F was the flow rate which of the outlet. Ca was the concentration of the outlet. Ca is the molar concentration. This is molar concentration. Okay, and this is volumetric flow rate. Phi and F are the volumetric flow rates. FCI, TCI were the coolant flow rate and temperature at the inlet of jacket, and this was FCO and TCO. V was the volume. So we saw some of the assumptions, and then we saw the overall mass balance equation. So d by dt, V into rho, and right hand side we had rate of input minus rate of output. So Fi into rho minus F into rho. So finally we got dV by dt is equal to Fi minus F. Okay, so this was the mass balance equation. Then the second equation of this CSTR modeling is component mass balance equation. So because this was an exothermic reaction will be those reactions which will release heat. Endothermic, which will absorb heat, right? So exothermic, because the heat is releasing from this, so that is why we are using coolant. Okay, so component mass balance equation, rate of accumulation of component A is equal to rate of input of A minus rate of output of A plus rate of generation. So here we had written the equation d by dt is equal to V into Ca. V is the volume, Ca is the concentration, is equal to rate of input of A. Fi is the volumetric flow rate, Cai is the molar concentration, and then minus rate of output plus rate of generation. Because in the equation we have rate of generation, but here the mass is disappearing. So minus of Ra is rate of disappearance, because in the equation we have generation. So that is why we have written here minus of minus Ra. Okay, right? So we had done till here. So after this we will go for this equation, right? This is the component mass balance equation, so I can write it here easily. Okay, so you can see here that rate of accumulation of component A, so this is V into Ca, d by dt of V into Ca. So we can differentiate this. Before this we can write the rate of reaction. So this minus of Ra, this minus of Ra is K naught e raised to the power minus E by RT into Ca. Ca is the concentration. Ra is minus of Ra is exactly the rate of reaction. Ra is the reaction rate. Okay, Ra is reaction rate, and here E is the activation energy. E is the activation energy. Okay, so activation energy is the minimum energy required for the reaction. So this is the minimum energy required for the reaction, and R here is the universal gas constant. R is the value of R is, I think, 8.314 something. This is the universal gas constant, right? So this is rate of reaction. So after we will complete this reaction, we will substitute Ra here. Okay, so now we will simplify this. So we can see that here we have two variables. So we will differentiate this. V and Ca both are variables. So we will differentiate this. So we can write it that Ca into dV by dt. Okay, so dV by dt we have already Fi minus F from the first equation. Okay. So because in the mass balance equation, we have got, what was the mass balance equation? dV by dt is equal to Fi minus F. This was the mass balance equation. Okay. So Ca into dV by dt, we can substitute Fi minus F here, and then we can write V dCA by dt. Okay, and then we will have here Fi, Cai, and so on, right? So right hand side we will write as it is. Then we will take some of these things to right hand side. So we can write dCA by V dCA by dt is equal to, so when we will take this Ca Fi minus F to the right hand side, we can take Fi common, and when we'll take Fi common, so we'll have Cai minus Ca. Okay, and then this minus F into Ca, this will be cancelled out, so this will be cancelled out, and then we will have minus of minus Ra, so we can write it plus Ra into V, right? Then what we can do, we can take volume also to the right hand side. So this will be Fi by V Cai minus Ca, okay, then plus Ra. So this is the component mass balance equation, and here we can substitute this minus of Ra. So we can write minus of then K naught e raised to the power minus E by RT into Ca, right? So this will be component mass balance equation for CSTR. This is the component mass balance equation for CSTR. So the first one was mass balance equation. The second is component mass balance equation. Now we will move ahead and we will write the third equation of CSTR. This is energy balance equation. Energy balance equation, right? So in energy balance equation, we will have rate of energy accumulation. So rate of energy accumulation is equal to rate of energy input. So the structure of overall equation will be same, and it will vary depending on the modeling equation which we are going to write. Rate of energy input minus rate of energy output, rate of energy output, then minus rate of energy removed by coolant, rate of energy removed by coolant, and then rate of energy added by exothermic reaction, rate of energy added by exothermic reaction. Exothermic reaction. Okay. So rate of energy accumulation. So d by dt is equal to, not is equal to, rate of energy accumulation. We have V, that is the volume, then rho, this will make mass, and then Cp, heat capacity, and then temperature. Okay, rate of energy, mc delta T. So reference temperature is 0 here. Okay, so rate of energy input, this is the volumetric flow rate, Fi, then rho, then heat capacity, Cp, and then Ti minus, reference is 0. So Ti is the temperature at the inlet. Similarly, we can write for the outlet also, F rho Cp. Heat capacity is also constant because already we have considered. So heat capacity and the density is constant already. So that is why we are writing rho and Cp at the outlet and at the inlet, right? So F rho Cp, then T, then rate of energy output. Rate of energy output we have already written. Rate of energy removed by coolant. So this, suppose this is Q, and then rate of energy added by exothermic reaction. So for this we will have to write minus delta H, and then minus RA, and then volume. So delta H here is, this is the heat of reaction. This is heat of reaction. And RA is reaction rate, V is volume. So rate of energy added by exothermic reaction is this minus of delta H minus of RA into V. Okay. So again we will have to differentiate this. Okay, and we can see here that some of the terms are common. So this V rho, and no, sorry, rho and Cp. So this we will cancel out, and for the remaining terms we will put this in denominator. So Q by rho Cp and delta H Ra into V by rho Cp. Okay, and we will differentiate what was the term which will remain here. So d by dt V into capital T. Right, so V is also variable, T is also variable, so we will differentiate this. So we will write here V d of capital T by dt, and then plus T into dV by dt, right? And what is dV by dt? This is from the mass balance equation. We know that this is Fi minus F, because at my table where there is very less space. So, okay, so V d capital T by dt plus T Fi minus F, and here we have Fi into Ti minus F into T, then Q by rho Cp plus delta H Ra V by rho Cp. If you write this in delta H form, that is also okay, because that will be, if you do not write, that is also okay, right? Then right, so Ft, this will be cancelled out, this Ft will be cancelled out, and we will have here V dt by dt is equal to, we will take Fi, and this will be Ti minus T, okay, then minus Q by rho Cp, and then we can write this in the original form, minus of Ra V upon rho Cp. We can take this V also in the right hand side, so there will be V here. We'll remove this V from here, so V rho Cp, and this will also be removed, right? So this is our energy balance equation for CSTR. D capital T by dt Fi by V Ti minus T, then Q upon V rho Cp plus delta H. And what is minus of Ra? Minus of Ra we can write K naught e raised to the power E by RT into Ca divided by rho Cp. So this is final energy balance equation for CSTR. Okay, so for CSTR we had three equations. The mass balance equation were in terms of volume dV by dt. The component mass balance equation was in terms of Ca dCA by dt, and the energy balance equation was in terms of temperature d capital T by dt, right? So this Q here also, the expression for Q we can write, this will be Q is equal to Fc, right? Fc is the flow rate of the outlet at the coolant, then rho C is the density, heat capacity, and then TCO minus TCI, right? So CPC is the heat capacity of the coolant, TCO is the outlet coolant temperature, and TCI is the inlet coolant temperature. Okay, so here what we can see here, what will be the input variables and what will be the output variables. So in case of this, so input variable will be what? The load variables and the manipulated variable. Okay, so because the reaction, this reaction can be controlled by this. The load variables are what? CAI is the load variable, Fi is the load variable, then Ti temperature, inlet temperature is the load variable, Q will be manipulated variable, and F outlet flow rate, this will also be manipulated variable. And what are the output variables? The terms which are in the equations. So these will be the volume, Ca and T. So these will be output variable. In this case, we can see the controlled variable and manipulated variable pairs. So for volume, we will have flow rate of outlet as manipulated variable, and for temperature, we will have Q, the heat removed by the coolant. Okay, so these are the three equations of CSTR, continuous stirred tank reactor. So mass balance, this was very simple, dV by dt is equal to Fi minus F. Then we had component mass balance, this, and then we have this energy balance equation. Okay, so all these three equations we'll be using in some of the topics. Okay, so
thanks for watching. Master Control. Master the future.